Okay, YouTube, this is my last video tutorial on solving equations in which we're going to comment on the nature of the solution sets that we get here, okay? And so, essentially, what I want you to know is that sometimes when you solve an equation, you get a statement that would be like always true. And what this would indicate is that the solution set is true for any value of x. In other words, it's infinitely large. Whereas sometimes we solve an equation, we get like, just one answer, okay? Or maybe not all answers, but we get at least one real answer. So it could be like the answers are x equals 2 and 3. We would say that, the solution set is finite. It has certain values in there. And then sometimes the solution set is just empty. There are no times you will get this equation to come out to be the way it is. That'd be saying like, when does 2 equal 3? Well, it never does. So in terms of vocabulary, let's go ahead and establish these facts right in the first place and talk about which one indicates which. But we say that identity equations, okay? These are equations that are true for all real numbers x. In other words, if I were to write the set of things that make this equation true, it'd be like all reals. Like every single one. It'd be infinitely large. But we say if they're true for all real numbers x, these are equations for which both sides of the equation are defined, okay? Or at least, okay, let me read this again. They're equations that are true for all real numbers x for which both sides of the equation are defined. Then we would refer to that as an identity equation. So something that is an identity equation, I give an example here, is like x minus 1 is equal to x plus 2 minus 3. And the reason why is because when you simplify the right side, we'd say that you get x minus 1 is equal to x minus 1. And solving this, that's actually what I want to do here. Let's go ahead and subtract x from both sides. Get all our x's on one side. You actually get the statement here that says negative 1 equals negative 1. So first things first, how do you identify an identity equation? We get a statement that is always true. Always true. And basically, if we said, well, then what are the solutions of this equation? Then you say all real numbers. You'd have to write it this way. We say, we could say, set builder notation, we say all x such that x is real. It doesn't matter what you plug in, you're going to get a true statement, okay? So now conditional equations, we say conditional things, it's kind of based on prior conditions, only under certain conditions. But we say these equations are equations that are not identities. That is, they're not true for all x values, but they're true for at least one. So an example would be like 2x plus 1 is equal to 3. If I were to subtract, say, 1 from both sides of this equation, I would get 2x is equal to 2. And it would follow that we could divide both sides of this equation by 2, and I would get a statement that says x equals 1. So our solution set here is not all real numbers, but there was at least one real number that when we plug it into this equation, we get a true statement, okay? So that would be what we refer to as a conditional equation. And then inconsistent equations. You can just remember inconsistent means no solutions. But we say these are equations that are not true even for not even one real number, okay? So the difference here is infinitely many solutions, one solution, or inconsistent would be no solutions. But an example of this is, when would 2x equal 2x plus 1? And if we were to subtract, say, 2x from both sides here to get my x's on one side, maybe off the right side, subtract 2x, we get 0 equals 1. And so the idea that I want to identify, inconsistent equations with here is this. We get a statement that is never true. So it is your responsibility to say that your solutions, if you're going to write the solutions, like we've been writing solutions up here. Here are our solutions, here are our solutions. Here you would say the empty set. Or we could say that the same way of writing this is, it's the set containing no elements, because nothing plugged in this equation will ever make that be true, okay? So what I'd like to do is I'd like to solve these following equations and then classify them as identity, conditional, or inconsistent, but also support our answer using a graphing utility. So with this first equation here, I don't know if anybody already sees it, but we get, after we simplify both sides, we get a statement that I'm going to go ahead and point out here. It's always a true statement. I mean, this is always equal to this. So this is an identity. But going ahead and using our methods for solving for x, if I subtract 3x from both sides to isolate my x's, you notice they cancel on both sides and I get negative 3 equals negative 3. So since this is always true, we say our solution, I'm going to write solutions in this case, is we're going to say x values such that x is a real number, okay? In other words, all real numbers x. And I said I do want to support this with the graphing utility. So what I'm going to need to do here is I'm going to need to go into y equals. I'll clear out these from my last problem here, and we'll type in both sides of this equation as different y expressions here. So we say y1 is 3 times the quantity x minus 1, and quantity, that's our y1. Our y2 will be the right side of this equation. We say 3x minus 3. And then the question becomes, well, how is it that we can identify? I'll hit zoom 6 here. How can we identify that it's true for all real numbers x? And you might be saying, well, where's the other graph? And what I want you all to notice is if I hit trace here and I hit up, down, up, 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 up. Here you're seeing it's popping between the curves. Essentially, these two equations would be equal at all values. They're on top of each other. These two graphs intersect everywhere. And even if I go look at my table, let's start our table at 0, and I'll go to table here. You can see that for all x values, you're getting y values that happen to come out to be the same. So that's why we're getting an infinitely large solution set here. Now looking at this next example, I look at this and I say, well, let's simplify the right side. We get 4x minus 7 is equal to 4x minus 4 plus 3. Combine like terms here, we get 4x minus 7 is equal to 4x minus 1. We'll go ahead and subtract 4x from both sides to get my x's on one side, but you'll notice that that causes my x's to drop out. And I get left with this statement right here, negative 7 equals negative 1. We know this isn't true. It's never true. So we say solutions. We'd say none. No real numbers. We would write the null set. Or we could write, I'm really bad at those cusps sometimes. We say the empty set. Okay. In other words, there aren't any x values for which when we substitute them into this equation, you get a true statement. So very quickly here, let's go ahead and take a look at how would that look like. What does it look like when you look at the solutions graphically in a tabular format, in a table? We say 4x minus 7, we'll put that in for y1, and then on the right side we say 4 times the quantity x minus 1. Oops, we need our 1. X minus 1 and quantity, that quantity plus 3. If I go hit graph now, we'll see these are all the solutions to the first equation. These are all the solutions to the second equation. And what you notice about these two lines is that they happen to be parallel. What that means is that they never intersect. What that means is there are never any x values for which the y values will be the same thing. And even looking at the table, we see that no matter what x values I use, negative 7, negative 1, negative 3, positive 3, 1, 7, they're always 6 apart from one another. They'll always be 6 apart from one another. So that's how we can graphically, in a tabular way, determine that this is a null solution set and that this would be an inconsistent equation. I suppose I'm supposed to write that. Inconsistent. Poor handwriting, I apologize here. Whereas this up here, we'd say that this is an identity equation. If we had gotten just a finite number of solutions, we'd say conditional.